In this video, we're going to start looking at electromagnetic waves. I've tried to give you a representation here of an electromagnetic wave. It's really difficult to draw these things in 2 dimensions. Your textbook has much better graphics than I could ever hope to draw here. But the idea is, if I have some sort of changing current, right? I have some sort of accelerating charge. Now, careful, I'm actually saying the same thing. What is a current? A movement of charges. Well, if a current is a movement of charges, then an acceleration of those charges will result in a change in the current. So I could say a charge is accelerating or a current is changing, either one of those. Well, if the current is changing, just by virtue of the fact that the current is made up of charges, then I get an electric field that is also changing in time. But, as implied by Faraday's law of induction, if I change an electric field, I generate some sort of changing magnetic field. Now, in this course, we haven't seen that explicitly, and we're not going to, but what happens when I change an electric field, I get an accompanying magnetic field which also changes. And so what I've drawn here is some sort of representation of the makeup of an electromagnetic wave which arises from accelerating charges or changing currents. It is composed of a magnetic field, which I've given here as B, which varies in time. It varies in strength, it varies in direction. I've tried to give you some arrows here to show you the direction here. But the magnetic field is changing in time. Right along with it, there's an electric field that changes in time. Notice they change in sync. I kind of got off the mark here, but when they're at a maximum, or I should say when one is at a maximum, the other is at a maximum. When one is at a minimum, the other is at a minimum. And when one is 0, the other is 0. So these things are actually inextricably connected, and you don't get one without the other. The direction here is also important. Notice how I've drawn them. I've drawn them perpendicular to each other, or orthogonal to each other. And that is how E and B fields are oriented in an electromagnetic wave. They are situated such that E and B are mutually perpendicular. Now, this is a wave, and so all of the wave characteristics that we know still come into play. It has a wavelength, it has a frequency, it has amplitudes. In this case, of course, the amplitude of the E field component is different than the amplitude of the B field component. If nothing else, they're just different in units. E field has units of volts per meter or newtons per coulomb. B field has units of Tesla. And so what we're going to see is that you can write down either the E field or the B field, and the form of the equations will be the same, but what actually goes into the equations will be a little bit different based on whether or not you write down the B field or the E field, and then we'll see how to connect them. But again, being a wave, it is traveling. So we have this E field which is varying in time, this B field which is varying in time, and the wave itself is propagating through space. So the propagation direction is going to be given along this axis. Notice that not only are the E field and the B field orthogonal or perpendicular to each other, they are mutually orthogonal to the propagation direction. This speed is going to be traveling with a speed, which we'll call c. Sometimes we call it v, but we're going to call this one c. The direction of c is perpendicular to the direction of E, perpendicular to the direction of B. They're all mutually perpendicular to each other. Okay, so this is an electromagnetic wave. One thing that might arise here is, what is c? What is the speed of these particular waves? Now, to do that, takes a fair amount of calculus and differential equations, but if you run through all of the math, which we're not going to, what you get, very interestingly, is this quantity here, 1 over square root of mu naught times epsilon naught. Now, what are these things? Mu naught is our magnetic permeability. Epsilon naught is our electrical permittivity. So you have this component that's associated with the magnetic field. You have a component that's associated with the electric field. This was actually a surprise when it was developed. They didn't call them electromagnetic waves back then because it wasn't really clear what happened, what was happening. But this clearly shows that something is going on between a magnetic field and an electric field. The surprise got even grander when this was calculated, because if you run these numbers, what you get is somewhere around 2.99 times 10 to the 8th meters per second, which is a very large number. That's about 3 times 10 to the 8th meters per second. This is, if you don't recognize it, the speed of light. Now, when that was discovered, that was very, very surprising, because electromagnetic waves were not, and the relationship between electromagnetic waves and light was not actually well known, but it was known that light, visible light, travels at this speed. And so when this was calculated, the inescapable conclusion is that light is just a kind of electromagnetic wave. It turns out it's a kind to which our eyes are sensitive. There are other kinds of electromagnetic waves to which our eyes are not sensitive. We just happen to be sensitive to visible light. But put all this together, it turns out light, what we call light, is just part of the electromagnetic spectrum. It travels at this speed always, and the speed of light is given by this equation. Let me remind you of a general wave speed, the general wave speed equation. In general, the speed of any wave is equal to its frequency times its wavelength. This is a general wave property. This is a specific wave property of electromagnetic waves. If you put those two together, of course, you can substitute c here for the velocity of the wave. So c for any electromagnetic wave is equal to its frequency times its wavelength. Therefore, if you know the frequency, if you know the frequency, you know the wavelength, because you always know the speed. The speed is always 2.99 times 10 to the 8th meters per second. If you know the frequency, you automatically know the wavelength. If you know the wavelength, you automatically know the frequency.